and welcome to the series on quantum spin. So I had a bunch of photos to be taken, so I'm dressed differently. But I was like, why not keep the same dress on? Because this is a pretty important topic in physics, so it's pretty important to be dressed formally. So yeah, let's get started. So I can't finish everything in one video, so obviously it's going to be a bunch of videos. But this is all you'll need to understand quantum spin, from the mathematics to the applications of what we learn in this video series. So without further ado, let's get started. I'll be using my notebook because these are my notes on quantum spin, because I don't want to go off track and waste people's time. So I want to keep it as crisp as possible. So let's get started. The topic being quantum spin. Okay. Now, to understand quantum spin, we need to understand a little more than what we're taught in high school in mathematics. So we need to have a working understanding of how vectors work. We need to have a working understanding of how complex numbers work, and a little more than that. So let's start with the mathematics, because when you want to read a novel, it's really important to know the language. So mathematics is the language of physics, and it's very important to know the basics at least. Okay, so let's start with vectors. So what are vectors? Vectors are physical quantities which have a magnitude and a direction. So they are represented by something like an arrow sign. Now the length of this arrow will tell me the magnitude of the vector, and the direction is given by where the arrowhead points. So let's take an example of vector, that will be velocity. So if my velocity is, let's say, 20 meters per second, this 20 meters per second east, this would be 20 units on the scale, and this would point due east. So that's how a vector looks like. Now if I take a vector in three-dimensional space, that's the space we live in, so we can denote three-dimensional space in mathematics as R3. So we call this R3, where R is the real number line. So if we take a real number line, it has values from minus infinity to plus infinity. So it will have values like 0, 1, 2, 3, minus 1, minus 2, minus 3, 3.4, minus 2.7, etc. If we add one more real number line to it, we get a 2D real space. So if we add one more real number line, we get a plane. Now if we add one more real number line, all mutually perpendicular, we get a three-dimensional volume, and that is the 3D space R3. Now if I take a vector, let's call the vector L bar. This L bar is a vector in the three-dimensional space. Now this vector will have components Lx, Ly, Lz. Why? Because if I have a vector pointing arbitrarily at any point in space, let's say I have this cube to denote my 3D space, and I have a vector pointing somewhere like this. So I can split the vector into its x component, that is how long it is along the x-axis, the y component, how long it is along the y-axis, and the z component, how long it is along the z-axis. So it's easier to write it in terms of its component of the Cartesian axes. So we don't have a random vector pointing in any arbitrary direction. We can resolve the vector into its components. That's what we mean by writing it as Lx, Ly, Lz. We're resolving the vector into its Cartesian components. Now, as we talked about, this is a three-dimensional vector. We can write this again as Lx I cap, Ly j cap, and Lz k cap. Plus. Now, what are these I, j, and k? Why don't we just write these funny capped symbols over here? Well, these are called unit vectors, or in mathematics we call them the standard basis vectors. So what are they? So these represent something which from which we can get the whole space, the whole vector space. In mathematics we call it a vector space. So if we have these three, we can regenerate the whole vector space only from these three. So it's kind of like how we have 1 rupee. If we add rupees, like 1 rupee to any n value, we can generate any amount. So our standard value, the lowest possible value to get the whole thing is 1 rupee, right? So if you want 1 crore rupees, you can add 1 rupee 1 crore times and you get the amount. If you want to add let's say 3000 rupees, you can add 1 rupee 3000 times and you get 3000. So our basis in the Indian system now is 1 rupee because the paisa has been removed. We don't have 50 cents circulating anymore in the system, so it's 1 rupee. So here you have these I, J and K vectors which can generate the whole vector space. So I cap is 1 0 0, J cap is 0 1 0 and K cap is 0 0 1. So these three, when I if I have a linear combination of these three, I can generate any three-dimensional structure I want only from these three. So these are called basis vectors. Basis, that's the term to note. Okay, so now once we're done with what bases are and what vectors are, let's move a little more into detail. So now we know what basis vectors are. Now let's talk about multiplying two vectors. So if you've taken maths in high school, you would know something called a dot product. Which says that if you have two vectors, let's say u bar and v bar, let's take u bar and v bar, and write v with a small curve over there so I can make sure it's v. So if I have u and v, if I write the dot product, it will be u dot v. This is how we represent a dot product. Now, if again, as I said, we can split each vector into its three components. So u bar can become, I can write u bar as ux, uy and uz, and v bar as vx, vy and vz. I can split them into these three components. Now when I take the dot product, all I do is I multiply each component with its corresponding counterpart. So ux is multiplied by vx, uy is multiplied with vy and uz is multiplied with vz, and you add everything up and that's a dot product. So u dot v or v dot u, it doesn't matter. So u dot v will be ux vx plus uy vy plus uz vz. Now why did I say it doesn't matter? It doesn't matter because there's a particular property associated with the dot product. It's called being symmetric. Because dot products are symmetric, if I swap these two, the value won't change. So u dot v will be equal to v dot u. This is what I mean by the vectors, the dot product being symmetric. So when I swap the sides, the value doesn't change. That's being symmetric, and this will also belong to the real number line. Okay. Because if I have real vectors, I can't get complex vectors. Now to make our life a little simpler, that is whenever we have some cases of where we might have vector multiplication, there are a few shortcuts which are beneficial if you can remember them. So these are the multiplication of the basis vectors. So if I have I cap dot I cap, this gives me 1. If I have I cap dot j cap, this gives me 0. If I have I cap dot k cap, this gives me 0. If I have j cap dot j cap, this gives me 1. If I have j cap dot k cap, this gives me 0. And if I have k cap dot k cap, this gives me 1. So from this we can make out that whenever you have the same bases multiplied into the same bases, you get 1, otherwise you get 0. So I cap is 1, j cap is 1, and k cap is 1. So j, k, j, all of them will be 0. Okay, so we're done with the shortcuts to remember the multiplication of the base vectors. Now when I say something like Vx, I mean V bar into I cap. If I say Vy, I mean V bar into j cap. And if I say Vz, I mean V bar into k cap. So this is how you represent the vectors as multiplication into their standard basis vectors. Okay, so now we're done with real vectors. Now this was all high school stuff. We've done all this in high school. How is quantum mechanics a little different from all of this? So if quantum mechanics were this simple, I mean it is pretty simple, but it's not so simple. It has a little bit more to it. It's just a little different. So how is quantum spin different? Well, the first difference is the vectors in quantum spin are 2-dimensional and not 3-dimensional. So we don't have these 3D vectors, we have 2D vectors. And they are not real vectors, they are complex vectors. So we said, this belongs to R3. In quantum mechanics, the vectors belong to C2. So C is the complex plane, or the complex, or the set of complex numbers. So let's look at what it means. So we can first write the two huge differences. The two differences, first, quantum spin vectors. I'm going to write QS as quantum spin vectors are 2D, not 3D. Second is QS vectors have complex components, not real. So this would mean they belong to the set of C2, not R3. Okay, so now we have the theory behind it. Now let's look at how they're denoted. So talk about the differences. Now let's talk about how quantum spin vectors are denoted. So you had in the real vectors, you had ij, k cap as the basis vectors. Here also you have the same concept of a basis vector. It's just that the notation is a little different. So in R3, bases are I cap, j cap, and k cap. In C2, that is the space we have for the complex vectors, the bases are spin up and spin down. This will be spin up and this will be spin down. So with I, j and k, we can get any real vector we want. With spin up and spin down, any linear combination of these two, we can get any quantum spin vector we want. So that is all we need. We just need these two. Okay, so these are the basis vectors. Now, what is this? What is this weird straight line and this arrow. Well, this is called a ket. K-E-T. Ket. These notations were like coined. The terms were coined by Paul Dirac, and he thought it would be a fancy way of calling them bracket. So you have the bra and ket. So this is the ket. So this together makes it a bracket. So as we said, we have, let's say, a normal real 3D vector. We can write this as Vx I cap plus Vy j cap plus Vz k cap. This is how you denote a real vector. Now a complex vector, a complex spin vector rather, can be denoted by a linear combination. A linear combination is when you multiply some value with your basis vectors. So you have the basis vectors as spin up and spin down. So I can multiply some alpha with spin up. So I can multiply this as alpha plus some other value with spin down. This will be, this has to be spin up, and this will be spin down. So any vector psi, let's take it as psi because we love psi in quantum mechanics because it denotes the wave function. So that can be represented as a linear combination of these two basis vectors. In real we have 3, in complex we have the 2 basis vectors, where you have obviously this belonging to C2 and alpha and beta belonging to C. Why is this C2? Because it is 2-dimensional complex numbers, and these are just simple complex numbers, so they are 1-dimensional complex. I mean, when you say C2, this means you have 2 complex numbers together. So that's why you have this belong to C2, and these are just random complex numbers, so that's why they just belong to C, not C2. Okay, so we are done with how we denote complex numbers with these bases. Now let's talk about how we write them. There's a fancy way in which we write them. So let's look at it. So let me just carve all this out. So as we said, we have, we talked about real vectors, I mean the basis vectors I cap, j cap, k cap, and we wrote I cap is 1 0 0, j cap is 0 1 0, and k cap is 0 0 1. Now we've written this as a row because it's all row wise. Now that is how we learned in high school, but the way physicists write vectors is always column wise. So we found it to be more helpful if we write column wise, I don't know, but so we write vectors column wise. So we had our 2 basis vectors as spin up and spin down. So to make our vector, we write them column wise. So we can write them as, we have the spin up vector as 1 0. So this is how it corresponds. This is what spin up looks like, and we have the spin down vector 0 1. So instead of writing them row wise, we can write them as column vectors, and that's the only difference. Mathematically it's completely fine if we write them as row wise, but there's a reason why I write as column wise, because it's easier to understand. Why? We'll come to it. So that's how you write vectors column wise. Now we come to something very, very important. Probably the whole field of quantum mechanics depends on that one mathematical operation. It's something called the inner product. The inner product. Now the inner product is something very similar to the dot product, just some small differences. So for now we can just take it as the dot product. So let's say we have 2 vectors, v and u. Now if we take, let's say, the inner product, we again get the same thing as Vx ux plus Vy uy plus Vz uz. So if we take a vector, let's say psi1, this will have its components beta1, beta1, this will belong to C2. So this was the real case. Now let's take complex cases because our work is mainly going to be with complex vectors. So if we have another vector, psi2, this will again have alpha 2, beta 2, and this will again be a part of C2. The inner product is represented using this very important notation. Without this, all quantum mechanics books are, I would say, incomplete. It is written as the inner product of V dot u. So if we have psi2 and psi1, we write this as psi1 and this belongs to C. So this is the inner product. This is the inner product of psi2 and psi1, and yeah, and this again can be represented with alpha and beta. How? Let's look at it. So all I have to do is I have to multiply this and this. So what will I get? I'll get alpha. If I take psi2 and psi1, I'll get alpha 2 bar plus beta 2 bar into beta 1. Now I'm sorry to rush it through, but there's a lot to cover, so I'm rushing a little bit. But this means that when we're taking the conjugate of alpha 2, the conjugate of beta 2, and multiplying it with alpha 1 and beta 1. We're not taking alpha 2, alpha 1, beta 2, beta 1, we're taking the conjugates. So this is psi 2 with psi 1. Now if I were to flip it, if I were to write it as psi 1 and psi 2, and here comes our difference with the dot product. The dot product, as we said, was v dot u was u dot v. It didn't matter. Here it does matter. Let's see how. So if I change it, if I flip this, if I write it as psi 1, psi 2, this will become alpha 1 conjugate alpha 2 plus beta 1 conjugate beta 2. So we can see that the conjugate vectors have changed, they are flipped. So there is a difference. Even though it looks like the dot product, it is not the same. When you flip stuff in the dot product, it doesn't change the final values. Here it does change the final values. So the inner product is, in mathematical terms, it's not symmetric, and this is how you write it. And we can write this alpha 1, the inner product of alpha 1 with alpha 2 is equal to the inner product of alpha 2 with alpha 1, the whole thing conjugated. So this is a very important relation, and this is how we build. This is the basis, no pun intended, for our whole subject. So now we come to something which is just a little more about vectors, and then we can talk about the juicy stuff of quantum mechanics. So we have something called a dual vector. So let's get to it. So we have the dual vector. Now what's a dual vector? Now if we have a normal vector, let's say a vector as we talked about psi, this is a vector, this has some alpha beta, and this is the column vector, this is called the ket. Now if we have a dual vector, the dual vector is what forms the bra part of bracket. So if this is the ket part, we need the bra part to form the bracket. So this will be the other part. So this will be alpha conjugate, beta conjugate. So when we write it together, it becomes a bracket. So let's write this as, if we take alpha 2, alpha 1, this becomes a bracket, and this will become now this is one column, one row, two columns. So we can write it in matrix form as row time column. So 1 cross 2. This is one column, two rows. So it is 2 cross 1. So whenever we multiply matrices, the end result is when we the end result has to be if you multiply these two, it will be 1 cross 1. So that will be the end result. So when we multiply them, we'll get alpha 2 conjugate plus beta 2 conjugate into beta 1. So when you multiply, so when you take the inner product of psi 2 with psi 1, this is what you get, and this is a 1 cross 2, a 1 by 2, 2 by 1. So when you multiply the matrices, it will become 1 by 1. Right. So now we're done with the maths part. Now let's talk about the physics part. We're going to use this, but most of our conversation now is going to be about the physics of spin. Okay. So when we talk about spin, in future lectures we'll talk about what actually means. But right now let's talk about measurement first, because it's very important to understand how the measurement and the probability part of spin work, to understand how spin actually works. So what spin actually is, we'll come to it in the later videos. But right now let's talk about something about the nature of the measurement of spin and how it differs in theory and in experiment. So experimentally we can only know if the spin is up or down. So we had those basis vectors, spin up, spin down. We can only know if it is which of the basis vectors it is. So if you can't have both together. So when you measure it, it has to be either spin up or spin down. Now in theory you can have the probabilities of how much each one is. So you can have the probability of how much it is spin up, how much it is spin down, and that is kind of analogous to the scalars we had which are multiplied to the vectors, the linear combination we had alpha and beta. So when you multiply something, we're technically scaling it, right? So in theory it is possible to find out the probability of how much spin up and how much spin down with respect to an axis. Okay, so that's what we mean by measurement, experimentally, and measuring spin, talking about spin in theory. Okay, so now let's talk about the actual process of measurement and how it works out. Okay, so we can write this as measuring spin, measurement spin. Now whenever we measure spin, for now at least, let's take one particular axis along which we measure the spin. So let's take the z-axis. So if I draw the z-axis, let's say this, and let's take an electron. So let's take the electron to be here. Now if I say that the electron, when I measure it, the electron, if the electron is so when I say I'm measuring this, it can be spin up or spin down. As I said, when I do the experiment, it has to be either spin up or spin down, and that will be with respect to the z-axis. So let's say this is the z-axis, and it has to be with respect to this. Now if I say if I write it as this psi, and if it is spin up, so if it is spin up, this will mean 1 0. This means it is 100% up, 0% down. As we said, it is only up or only down. It can't be together. It can't be both. So if we measure it to be spin up, it is 100% up and 0% down. Similarly, or conversely, if it is measured to be spin down, it means it is 0 1. It means 100% down and 0% up. So this is what I mean by when you measure spin, it becomes this. Now we can say, okay, this can be alpha, beta, so yeah, that's just the notation of the spin vector. So if I measure to be spin up, it has to be 1 0, 100% up, 0% down, and if it is spin down, it is 0 1, 100% down, 0% up. Now, as we said, we'll talk about the theory as well. So we talked about experimentally what happens. Now let's talk a little bit about the theory of what happens. So if I express the spin vector psi as a linear combination of spin up and spin down, this is now if I measure, if I write it like this, there's something called the probability of it being spin up, the probability of it being spin down. Now when I take the value of alpha, if I take the absolute value of alpha and if I square it, I get the probability of the particle, electron, fermion, I mean electron, muon, tau, neutrino, any particle, is the probability of it being spin up. That will be alpha squared, mod of alpha squared. If I take beta squared, it's the probability of the particle being spin down. So this is the theoretical part of it. When we talked about experimental, we just talk about spin up or spin down, and we're not bothered anymore. If we talk about it theoretically, we need to talk a little bit more about how much of it is likely, like how likely is it to be spin up, how likely is it to be spin down with respect to a particular axis. That is very important. It has to be with respect to a particular axis. It can't be arbitrary. So whenever we define it as spin up or spin down, it is with respect to an axis. So here we took the z-axis for example. So this will give you this alpha squared term, the mod of alpha squared term. That is the probability of the electron or muon or tau, whatever particle, being spin up, and this will give you spin down. Now we need to prove. Okay, so what is maximum probability? What are the chances of something happening all the time? 100%, and right. So we have probability equal to 1. So if this is some probability and if this is some probability, and either one can happen, then together they should be 1, right? So we can say that alpha squared plus beta squared is equal to 1. This is a very important identity. And so we can say that the inner product of psi with psi, which is equal to alpha conjugate beta conjugate alpha beta, the dual vectors, which will be alpha conjugate alpha plus beta conjugate beta. This will be alpha squared plus beta squared, which will be 1. So the inner product of a wave function with itself is 1. That's what we've come at, because we've taken it, we've multiplied it with, alpha star, alpha beta, we write the components, expand the matrices, alpha squared, beta squared, and because we know it has to be 1, we've proven that it's equal to 1. Okay, so we talked about the properties of it being up or down. Now, as I said, it has to be along a particular axis. So if we again take the z-axis, we can write it in terms of alpha and beta. So probability of, let's say, of the electron being spin up with respect to the z-axis will be, I can write this as, this is the notation I can write as, how did I get this notation? Well, there's a very simple logic. If I take the spin out and this, I get 1, 0. If I want to write this as a dual vector, so I'm writing this as a dual vector, I can write this. We know that spin up is 1, 0. So spin up was 1, 0 because we were writing. If we write spin up as a ket, it is 1, 0. Right now I'm writing on the left side, so I'm writing the bra part. So I'm writing it as a row. Now we know psi is alpha beta. So when I multiply these two, this multiplies with this multiplies with this, so I get alpha. Similarly, if I have spin down, this will be 0, 1 alpha beta. So this will give me beta. 0 multiplies with alpha, 1 multiplies with beta. So I get this. So if I take the square of this, I will get alpha squared. Similarly, if I take the square of this, I will get beta squared. Now we've talked about measurements along the z-axis. When we have z-axis, we took it as 1, 0, 0, 1. Now what about other axes? As I said, it's very important to define what axis we're taking the measurement with respect to. So we took it along the z-axis and we got the values we just talked about. Now if we take other axes, let's say, we talk about all three in general, like x, y, z. So let's talk about them. I just dropped my cap. Yeah. With respect to all axes. So if I have spin up with respect to x-axis, my vector will be 1 by root 2 and 1 by root 2, the column vector. If I have spin down with respect to x-axis, I will have 1 by root 2 and minus 1 by 2. The only thing we change is the minus sign because it is spin down, so it is the reverse of it. So the minus part will change. This is along the x-axis. Now if it is along the y-axis, if it is spin up along the y-axis, it is 1 by root 2 and I by root 2. This is where we first encounter I now, amazing imaginary number. If it is spin down with respect to y-axis, I'll get, can you guess, if it is 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2, if this is 1 by root 2 and I by root 2, we are flipping the particle along the y-axis, so there should be a negative sign, because if it is spin up, it is positive, spin down will be negative in the same way. So this will be 1 by root 2 and this will be minus I by root 2. And along z-axis we already talked about, if we have spin up along z-axis, we say it's 1, 0, and if it is spin down along the z-axis, we say it is 0, 1. Now, why are we taking all these weird values? How did these weird values come? Like, why is it 1, 0, 0, 1? Why is it 1 by root 2, I by root 2, 1 by root 2, minus I by root 2? How did these values come? These values came from this relation which we talked about. This very important relation. This has to be satisfied, and that's why we get all these values. These values satisfy this, and so we take these values. How? Let's check if it actually satisfies it. Okay. So if we take the property, let's take x spin up x, it's inner product with spin up x. This basically gives us, it's just a different way of writing this. So this should be equal to 1. Now let's check if it is equal to 1. So we had 1 by root 2 and 1 by root 2, and we have 1 by root 2. We are writing in terms of dual vector, so we get this. So we get 1 by root 2, 1 by root 2 plus 1 by root 2, and 1 by root 2 you get half plus half is equal to 1. Satisfied. So the condition is satisfied for spin up along x, spin up along x. Now let's try spin up along y and spin up along y. Let's see if that works. It does work, but let's just see it for our satisfaction. So let's change x to y. Spin up y, spin up y. So along y, it was 1 by root 2, if you can remember, and the second part was I by root 2. Now, because we want to write as a dual vector, we will write because we take the complex conjugate. Over there, the minus root 2 became plus root 2. Here, the minus root 2 will stay the same for the first part. So, it will become minus I by root 2. And this will become 1 by root 2. And because the other part is, minus of that, it will become the conjugate. So, it will become I by root 2. Which will give me 1 by root 2. 1 by root 2 plus verified. Now, as we said, this will work, and for z it's a trivial case. This is 1, 0, 0, 1, so it will give you 1. Now let's talk about what if we flip one of these. So if we take spin up y and spin down y, so there is a way to guess. We have to recall our properties of vectors, but you can work it out. So if we do up and down, it will be 1 by root 2 mean this is subtracted from this. This is just, it is written as a vector, so it's not subtraction from this. This into 1 by root 2, and because it is spin down, I won't change the sign. I'll keep it as minus I by root 2. If we multiply, we'll get 1 by root 2, 1 by root 2 plus minus I by root 2 minus I by root 2, which gives me half minus half, which is 0. So this is a very powerful tool we have. With the dual vector multiplication, we can find out the inner products of any vectors we like. So now let's take a question. So let's apply the skills we've learned to a question. Yeah, by the way, the property that you measure along, the property of spin up, you measure along the x-axis is given by how we denote it. The property you measure of the particle being spin up along the x-axis is given by this. If you want to measure the property for spin down, just write this, and the same for the other axis as well. This is how you denote it. This is the notation for the property of finding a particle spin up along the x-axis, and that is, it will always be squared, right? So now let's take a question. Okay, so if we have, or better still, let's just understand one more term which is related to this topic. So if we have something like a combination, let's take these are two different axes, so we need to multiply their respective basis vectors. So we'll get we take this and we square it because we're going to find the absolute value. So we'll get 1 by root 2 because the first one multiplies into this, second one into this, so it's 1 by root 2 squared. This is 1 by root 2. So this is 50%, right? Now when we say 50%, it is a very important number in statistics. So we can express this if you want to write, if you want to, let's say, express this, the ket part of the vector being spin up along the x-axis, we can write this as a linear combination with respect to some other axis. How? I can write this as 1 by root 2 I'm expressing this as a combination of spin up of z and spin down of z. Why can I do it? Because it works out mathematically. Because if you compare the bases, this will work out to this. So because I'm expressing 1 as 2, I can say that this is a superposition, because there are more than one states. By the way, these are called states. So I have one state, it is expressed as a combination of two states simultaneously. So this is a superposition. This is mathematically what a superposition looks like. So this is a superposition. Now so let me just write this as, I can include this is a now we also know what superposition looks like. So the spin up state along the x-axis is in a superposition of the spin up state along the z-axis and the spin down state along the z-axis. That's what this means. Now if we take a real life problem, or let's take an actual numerical problem and try to apply the skills we learned. I was going to do that, but I just thought of mentioning this point about superposition as well, as it might be helpful. Okay, so let's take, I've given one quantum state. This that part is called state. We're given a quantum state. It is 3 by 5 plus I times 4 by 5. Now let's say I've asked to find the property of spin up along x, spin up along y, spin up along z, spin down along x, spin down along y, and spin down along z. So all the possible spin properties along all the three axes. So how do I go about it? I've been given this expectation value and trying to find the properties with this. How do I do that? We have this is a fundamental relation. This will be the components written as dual vectors. If I multiply this, I'm verifying if it is actually legit. So why do I check it? Because it should make sense, right? So it will only be a proper quantum mechanical state if the inner product of this with itself is 1. So I'm checking if this is going to give me 1. So I first check it and then I find the other properties. So this will multiply that, so that will give me 9 by 25, and if I multiply I squared will be -1 plus 1 plus 16 by 25. This will give me 25 by 25, which is 1. So it's satisfying the condition, so it is a proper question. So I have just verified if the question is not wrong, so it is correct. Now let's find the probability along the x-axis being spin up. How do I do that? Well, as I said, we have to write it in a certain way. That will be probability of the particles along the x-axis being spin up, the inner product with psi, this thing whole squared. So this is how I write probability of the particle being spin up along the x-axis. So all I have to do is again just apply the mathematics. So I take the basis vectors of x. So it will give me 1 by root 2, 1 by root 2, and now I will take the basis vectors for psi, and they have given that to me as 3 by 5 and I 4 by 5. So I'll just plug them over here as 3 by 5 and I 4 by 5 square. So I will get multiply this into this, so I'll get 3 by 5 root 2 and I 4 times I into 4 times 5 root 2. We have to square each term, so it will become 5 into 5 squared, 25 into root 2. So root 2 will become 2, so that will give me 50. So this will become 9, 25 into 2 plus 16, 25 into 2, which will give me 25 by 50, so 50%. So the probability of finding the particle spin up along the x-axis is 50%. So we found 1. Now we are going to find all 6. Now as we know that alpha squared, we learned this, alpha squared plus beta squared is equal to 1. Now I can use this to find that if this spin up is 50, spin down has to be 50 for it to make it 100. Now I can obviously do it the long way. I can write y with, I can write this as spin down and do the multiplication again. But why waste time when you know it? So I can just directly write this as 50% of it being spin down with respect to x. Now we have to find it with respect to y. So if you want to just confirm it, if you want to prove it, you can do it. Let me just do it for the satisfaction of people. So x psi, this will be 1 by root 2 minus 1 by root 2 multiplied into what are they given? 3 by 5, right? 3 by 5 and I 4 by 5. So this will give me 3 by 5 root 2 squared and minus 1 times I squared I 16 minus 1 plus 1 by 5 root 2 squared. So give me again same thing, 9 by 25 2 plus 60 by 25 into 2. So again give me 50%. So I've just verified that the maths does hold true. Let's find for y and z. We found x, let's find for y. So spin up y. So I have to take the basis for y, multiply it with this and square. Same logic, 1 by root 2 minus I by root 2. This will be 3 by 5 and I 4 by 5. I have to square this whole thing, which will give me 3 by 5 plus minus. This will give me 49 by 50. This is 98%. Whoa. So we just found out that the probability of the particle being spin up with respect to the y-axis is 98%. So it's a very high probability. Now, are there any clues which we might get from this that it will be very high? Yes. So if you look at it, the expectation value is pretty similar to the basis vector for spin up of y. You have I, which we have, so we know that it has something to do more with respect to the y-axis. So because of this I part, we know that in either of the directions it's going to be higher with respect to the y-axis. So the other spin down will just be 2%. Now let's do z-axis. So spin up, same thing. I can directly multiply this as 3 by 5. So got 9 by 25, so if I'm going to convert this to 100, I'll get 36 by 100. So 36%. And the reverse for spin down, so it will be 64%. So now we know how to find the probabilities of spin up, spin down, etc. Now we come to another important part of theory, which is the act of measurement and how it changes the behavior of a system. So when I said that you have a state, let's say this is a state. This is a linear combination of alpha and beta. So you will have alpha times spin up and beta times spin down. Now when I'm making a measurement, I know for sure it's becoming either alpha, like either spin up or spin down, because as I said, experimentally we can only have those two possibilities. So if it is up, I know that this psi is becoming this, and if it is spin down, for up it's becoming this, for down we know that this is becoming this. We're finding out. So what does it mean? This means that we are collapsing the wave function. Again, that's a big word, but there is nothing complicated. It's just very intuitive to understand if you look at it using the graph. So let's say, again, as I said, you can represent vectors as combinations of the components. So if we have this as being spin down and this as being spin up, our quantum spin vector psi is, let's say, a linear combination of these two. So it's going to be something like this state. So it will have some amount of spin down, some amount of spin up. Now when I measure it, it's either becoming this or this. So it is collapsing, it is falling onto either the x-axis or the y-axis. So I can visualize it as it's falling onto either the x-axis or falling onto the y-axis or x-axis. And that's what I mean by collapse of the wave function. What does this tell us? So this tells us if I measure, let's say, the spin of a particle with respect to the z-axis, and I find it being spin up, and if I keep measuring it along the z-axis, it's going to remain as spin up. It's not going to change. So the measurements if I make are going to be constant if I keep measuring it along the same axis. Now if I change the axis I'm measuring it, so I measure along the z-axis, I found it to be spin up. So we from theory we know that 50% of the time it can be spin up or spin down if I am changing the axis. So I measure it to be along the z-axis spin up. Now if I measure it along the x-axis, theoretically 50% of the times it will be spin up with respect to the x-axis, and 50% of the time it will be spin down with respect to the x-axis. So I measure, let me just write that down to make it clear. I have a particle, I measured it with respect to z axis. Now I found it to be spin up. Now if I keep measuring this along the z axis infinitely, it will always give me spin up. Now if I measure this, so it will spin up 100% of the time. Now if I measure this with respect to let's say the x-axis, it will be 50% of the times spin up and 50% spin down. Now when I measure it, I'll find it to be either one of these two. now, so once I've measured, let's say I find a piece spin down over here with respect to the x-axis. Now when I measure it again with respect to the z-axis, it is not always 100%. It can be either 50-50. So it can either be spin up or spin down. So when I change the axis, I'm also changing the initial condition where it was with respect to the z-axis. So changing the axis with respect to your measuring destroys the previous measurement. And yeah, that's about it for spin for now. I guess we've covered a lot of topics for the first class, and I guess yeah, that's all for today. Thank you for watching.